A particle moves with simple harmonic motion about a point O. The particle starts from its extreme position and first reaches a maximum speed of 6 meters per second after 4 seconds. Question A, Part A. State the period of the motion. In Part B, hence or otherwise calculate the amplitude of the motion. Now the period of the pendulum is the time it takes to go back to where it started. So if it starts at one extremity, goes through its oscillation and goes back to where it started, that's called its period. Now let's look at this example here. As you can see, on the way down it's accelerating until it reaches its fastest point. That takes 0.4 seconds. Then it decelerates on the way up until it gets to its highest point. That takes us another 0.4 seconds. Accelerates on the way down until its fastest point. It takes us another 0.4 seconds, and from its fastest point back to where it started took another 0.4 seconds. So the period of this pendulum is 4 times the time it took to get from the extremity to its fastest point. 4 times 0.4 is 1.6 seconds. Now in our case, our body undergoing simple harmonic motion took 4 seconds to get to its fastest point. Therefore it shall take 16 seconds to go back to where it started, and 16 seconds is the period of our body in the question. In Part B we're asked to find the amplitude of our body undergoing simple harmonic motion. Now amplitude is the distance between the centre point where it was going at its fastest to its extremity from where it was released. Now we have 2 pieces of information that helps us solve this problem. First of all, we have the period, 16 seconds. This is something that we have got no control over. Once we have chosen our apparatus for simple harmonic motion, the period is fixed. For example, if it's a pendulum, you want to change the period, you have to make the string shorter or longer. If it's something on a spring, for example, undergoing simple harmonic motion, you would have to make the spring stiffer or less stiffer. Only those things will change the period. From where it is released, that won't change the period, but it will change the speed at which it's travelling through the centre. For example, if I wished my pendulum to go very, very fast, I just release it from a greater extremity. Now if we're doing the exam, this problem can be solved in seconds. If we look at page number 31 from the arrangement booklets, we can see that the maximum velocity is equal to the amplitude multiplied by the angular frequency. And the angular frequency can be found by 2 pi divided by the period. Then you get an answer immediately of 15.3 meters. Then you can go on to the next question. And that is how you'd approach the question in an exam, armed with those 2 formulas that you may have memorised. But if that's all we know, and we don't really know the background behind these 2 formulas, where they came from, we're living in a world of vagueness, and we're not, even if we get the right answer and we get our qualification and that entitles us to go to university, we won't be as prepared as we think we are, and that can lead to problems. So now I'm going to show you a wee bit of the background behind these 2 formulas. The first question you might ask is this: well, if I've got something going backwards and forwards undergoing simple harmonic motion, how can I associate an angular frequency with that? I don't really see what angles there is there to be measured. Good question. Let's look at this piece of apparatus. Now I've got a turntable going round and round and round, and I have got a marble attached to it, and I can see the shadow of the marble on the wall. As that goes round and round and round and round, we know we can associate with that marble an angular velocity divided by angular displacement divided by time. So if it's over a complete revolution, this angular velocity will be 2 pi radians, the angular displacement divided by the period, the time it took to go the way around. That gives you your answer. Angular velocity. Now I've also got a pendulum. Now if I release that pendulum, at the instant it's above the marble, when the marble gets to it, and I look at their two shadows, their shadows will be in sync. The shadow of the marble will always be below the shadow of the pendulum. If I can judge it just absolutely correct, and I make sure the period of my pendulum matches the period of the body going round and round. Since they're in sync, the shadow is executing simple harmonic motion. This means we can associate simple harmonic motion with circular motion. And this is where our angular velocity comes in. And this is a clearer illustration of this. As a colour ball goes round the circle, the pink ball that's attached to it goes up and down, undergoing simple harmonic motion. And this is how we can associate simple harmonic motion with circular motion. But where the colour ball has got an angular velocity, where does the angular frequency come in? Because when it comes to angular frequencies, we're normally speaking about waves. In this illustration here, we can see how the pink ball going up and down cuts out or traces out a sine wave. The angular frequency of that sine wave is exactly equal in magnitude to the angular velocity of the colour ball going round and round and round. And this is how we can associate simple harmonic motion, something going backwards and forwards, to circular and sinusoidal motion, which gives us a greater insight into what these things are and helps us solve problems. Now we've got some background out of the way, we're now in a position to solve our problem. The famous condition for simple harmonic motion, and that's provided in our arrangement document on page 31, is a second order differential equation. It states x double dot is equal to negative omega squared times x, where the x double dot says we have to differentiate our function x with respect to time twice. X is displacement as a function of time. So what we are asked to do is this, or what we have to do to meet the condition for simple harmonic motion is to find some displacement as a function of time and differentiate it twice. And if you differentiate it twice and you get back to the same function multiplied by a constant called negative omega squared, then that function executes simple harmonic motion. Two functions do it, the cosine and the sine. If you've got cosine theta and you differentiate it once, you get negative sine theta. If you differentiate negative sine theta, you get negative cos theta, I should say. Know that. However, our theta has to be a function of time. Well, that's easy enough because theta is equal to omega times t. Remember, these are moving. This thing is moving. So we've got something in motion where theta is equal to omega times t, where omega is the angular frequency and time is the position of time we're looking at. Therefore, x is equal to cos omega t or sin omega t. Either of those will do. And now remember, if cos omega t satisfies the equation, then multiples of it will also satisfy the condition. Therefore, x is equal to a cos omega t satisfies the condition. Displacement is equal to a cos omega t, where a we don't know, but we do know what omega is. That gives us this graph, this cosine graph, and that cosine graph will tell you the displacement of our body undergoing simple harmonic motion at a certain time. For example, if you look at, we were told its displacement was equal to 0 going into the fastest speed after 4 seconds. And if you put 4 seconds in the formula, you do indeed get 0. So here we've got a displacement function that satisfies the condition x is equal to a cos omega t, where omega, remember, is pi over 8. Where does the velocity come in? What we want to find the amplitude A, we don't know what that is. We do know what the velocity of the thing is going at its fastest point. Well, we know this. If we differentiate a displacement function, we get a velocity function. So when we differentiate x is equal to a cos omega t, we get negative a omega sine omega t. And we can see from this graph that the maximum velocity is given by a 5/8 meters per second, and that's equal to 6 meters per second as given in the question. Solve that for a and we get 15.3 meters as we worked out earlier. Well, I hope you enjoyed the video and I hope you found it useful. If you did, give it a like. Question number 5 is coming shortly. Thanks for watching the Young Scottish Physicist.